Hello everybody once again. This is the final lesson on the Stats and Mechanics book. It's the final lesson on the final chapter, variable acceleration. And so once we've done this, it's a case of revision and hard work and recapping to make sure you've understood what's come before it. So well done for getting to this stage. So regardless, there's always going to be some warm-up questions to have a go at, so let's have a look at those now if we can. 4 questions this time, so try them first and then only look at my solutions once you've attempted every single question and give it your best shot. Once you've done that, then play this video and just see what answers I'm giving to make sure yours are the same as mine, and if not, try and work out why not. So let's have a look anyway now at the solution to question 1. So question 1, we have a particle moving in a straight line, accelerating uniformly, that just means constant acceleration, from a velocity big U when t equals 0, to a velocity of big V at time big T. Draw a velocity time graph for the journey described. So what we need first of all is a pair of axes, and to realise that constant acceleration on a velocity time graph means a straight line with a positive gradient if the speed is increasing. So what we need is something a little bit like this, with velocity on the vertical axis and t on the horizontal. And so the straight line implies positive acceleration. And so now we need to look at these initial conditions. So we're told here that when time is 0, the velocity is big U. So we can label this on now. We're also told at time big T, the speed is V. And so here the speed is V, and the time here is big T. So just to make it clear, I'm just going to do a dotted line to show what I mean at those points, just in case people are having trouble reading it. So down here, that's time big T, and reading across, that's a particular velocity big V. And so that'll do for a sketch of the velocity time graph, just filling in the conditions of big U, big V, and big T. For question 2, we're told that the acceleration is rate of change of velocity, so let's find an expression for the acceleration of the particle from question 1. So let's just go back to first principles about what acceleration is. So acceleration, little a, let's just write this down. So acceleration a, it's the change in velocity, so delta v, divided by the change in time, which is delta t. And so if we were to go back to our graph for a second from the previous page, what's the change in velocity from time being at the start to the time being at the end? So if I just toggle back for a moment, the change in velocity, it ends up being big V, it starts being big U. And so the change in velocity between here and where it starts, that must be big V minus big U. So the change in velocity is big V minus big U, and the change in time, the final time is big T, the start time is 0. T minus 0 just gives us big T. Then from part B, we can rearrange this to show that V equals U plus AT, where we've got particular values of V, U, and T, where they're all big. And so if we've got that A equals V minus U over T from part A, we can multiply both sides by big T. So A big T equals V minus U. We can now add U to both sides, and we get U plus AT equals big V, which is essentially the same as what we want to show, only here V is a subject. So let's just switch the order, make V the subject. Therefore, big V equals big U plus A big T. And that's question 2, polished off. Question 3, show that the area under the graph from question 1 can be expressed as T over 2 brackets U plus V. And so let's just remind ourselves of the graph from question 1, which is here. And so we need to work out the area under this graph. And so what we're wanting to work out here is the particular area under here, which I'm going to shade in this lovely yellow colour. Well, I think it's lovely. If you don't agree, then that's fine. So maybe I should have called this in before, but hey ho, forgive me. So we need to work out this area here. And so the area under the graph, what sort of shape do we have? So it's a trapezium, isn't it? Area, so it's going to be the area of a trapezium. So just going back to basics, GCSE level or even before, how do you work out the area of a trapezium? Well, what we need to do is the two parallel ends added together, and so it's going to be this bit plus this bit here. So we can actually draw this on to make it clearer. So we need to work out that line and that line. So it's u plus v. This is u, this is v. And the way I used to think of the area of a trapezium is it's the average length multiplied by the height. And so we add these two together, u and v, then divide by 2, and then multiply by the height, which in this case is the length, because it's like a trapezium on its side. So the length of it, from 0 to t, is just t. So this is how I'd write it if I was teaching maybe a GCSE research class, which is absolutely fine and is still correct. We can neaten this up here, because we're dividing by 2 and tangent by t. That's the same as taking t and dividing by 2. Then we can put the brackets on the end. We're allowed to do that. It's still exactly the same. So that's exactly what we wanted to prove. Question 4. Given the area under the VT graph represents the displacement at time t, we can use the answers to question 2 and 3 to show this. So let's prove that this can be shown easily enough. And so just reminding you what we had from question 2, we proved from question 2 that v was big U plus a big T. So I'm just going to put that to one side. We're going to use that in a moment. And so from question 3, we also had that S was big T over 2 U plus V. So it's all going to come together to prove this. And so if we have now that big S is T over 2 U plus V, if you notice what we're trying to prove here has no V in it, so what we need to try and do is eliminate this V. And so where have we seen V before, a different expression for V? Well, V is U plus AT, isn't it? So what we can do is we can substitute U plus AT for this V here. And so if I just swap away the V and pop in instead of it this U plus AT, then we're getting closer to what we want to prove. So now we have U plus U. So this bracket can be neatened up. U plus U, that's going to be 2 U's plus A multiplied by big T. Now we can expand out these brackets. So T over 2 multiplied by 2 U's, the 2's are going to cancel, and we're just going to be left with big U, big T. And plus T times T is going to be T squared. So we're going to have AT squared all divided by 2. So we're going to have a half A big T squared, which is exactly what we wanted to prove. And so we've proven that big S equals big U big T plus half A big T squared. We can now also show, using integration, that V equals U plus AT. And so if we just set up the problem clearly first of all, and just say that we're imagining a particle moving in a straight line with constant acceleration A. The initial conditions are when the time is 0, the velocity is little u, and its displacement from the fixed origin 0 is 0 meters when the time is 0. So using those conditions, we can now prove, using integration, not that V equals U plus AT. So if we remember from a previous lesson how we can use integration to get the velocity from the acceleration, you should remember, hopefully, that the velocity is always going to be the acceleration integrated with respect to time. And so if the acceleration is constant, which it does say here, it's constant acceleration a, we're just going to be integrating a constant. So if we integrate the constant a with respect to time, we just end up with the product of the constant and with what we're integrating with respect to. So that's just going to give us at. However, we also need to include the constant of integration each time. But because we're given these initial conditions, we can now work out what big C is, this constant of integration. So we've been told that when the time is 0, the velocity is u. So if we now just input these initial conditions into this expression for v, so instead of v we're going to put u equals a multiplied by 0 plus c. In other words, u is 0 plus c, so therefore we know that u must be the same as this constant of integration. So now we know that this constant of integration is u, we now have v equals at plus u, or writing it the more familiar way, we have that v equals u plus at. And so we've derived, using calculus, the expression that relates v, u, a and t. This, one of the first u+at formulae you will have ever seen. For part B, we now use what we found out from part A to derive s equals ut plus a half at squared. So we need to recall that the displacement is obtained by integrating the velocity with respect to time. And from part A, we now know that velocity is the same as u plus at. And so we can integrate u plus at with respect to time. Now u is just a constant, it's just a fixed number, which means the initial velocity. And so we can treat u as a constant and integrate that with respect to t. That just gives us u multiplied by t. A, we've said here, is constant, so again a is constant, so integrating t with respect to itself gives us a half t squared. So with this a included, that gives us a half a t squared. And then of course we have to include another arbitrary constant of integration, which we can now work out based on the initial conditions. And so we're told at t equals 0 here, its displacement from a fixed origin is 0, and so we can input this to work out c. So if we just say here that when time is 0, when t is 0, the displacement from this fixed origin is 0. So going forward, we can say that s, which is 0 at time t equals 0, equals ut, which is u multiplied by 0, plus a half a t squared, which is now a half a 0 squared, plus c. So 0 equals 0 plus 0 plus c, so therefore c, we've concluded, must be equal to 0, and therefore we then have s equals ut plus a half at squared, which we've become familiar with using before now. So that's how it can be derived using integration. I want to now show you a slightly harder problem involving kinematics using calculus. So this is one I've just created. I've derived it from a textbook, to be honest. So I want you to imagine now I've got two different sports cars, an Audi and a Bentley. I've picked those because it's just A and B. Not very imaginative, I know. So we're having some time trials along a section of a straight road with two tracks. So one track goes one way, another track is moving in the opposite direction, so the cars don't collide. So for a section of this straight road, the cars are racing in opposite directions, one going one way on one track, the other going the other way on the other track. The Audi passes point A and travelling towards point B at time t equals 0, and the distance from A is given by s equals 100t minus 2t squared. And so because we're talking about an Audi and a Bentley, I might just include here actually s subscript a, just to denote we're talking about the Audi. So part A, we need to find the time when the Audi reaches point B. Point B is where it comes to rest and stops. Okay, so this Audi is going to stop when its velocity is equal to 0. So that's what we need to solve now. So we can now just say the Audi reaches B when V equals 0. But what does V mean? Well, V is ds by dt. The velocity is what we get when we differentiate s with respect to time. Velocity is the instantaneous change in displacement with respect to time. So V is ds by dt. So we need to differentiate this here. So differentiate 100t, we just get 100. Differentiate 2t squared, the 2 comes to the front and multiplies a minus 2, so we get minus 4t to the power 1. So that's going to be set equal to 0 when the Audi stops. So this is actually a fairly easy equation to solve. In fact, very easy. So when is 100 minus 40 equal to 0? Add 40 to both sides. We get 40 equals 100. Therefore, the time must be 25 seconds when the Audi stopped. Don't know if I put a capital letter for stops, but there you go. So we can use this now for part B. So for part B, using the answer to part A, I'm just going to remind ourselves before we get started that the Audi stops after 25 seconds. So we need to work out the distance from A to B. So it stops at B after 25 seconds. Okay, so we've got here a expression for the displacement. So we now know the time when it gets to B is after 25 seconds. And so the displacement when it gets to B is just substituting in the t value of 25 seconds. And so AB, from A to B, actually no, I'll just leave it as AB. AB is 100 lots of when t is 25, so 100 times 25 minus 2 multiplied by 25 squared. So if you try this on a calculator, 100 times 25 minus 2 times 25 squared, you should hopefully see, like I'm seeing here, that the distance must be 1250 meters for this straight stretch of road AB. For part C, I need to use calculus to show that the Audi travels with constant acceleration. So what we can do first of all is to go back to part A when we worked out what the velocity of the Audi was. So let's just recap. We've got that the displacement of the Audi is 100t minus 2t squared. I'm not doing anything here apart from just copying down what's already written here. So the velocity of the Audi, which was just the change in displacement of the Audi with respect to time, we differentiated that in part A and got it was 100 minus 4t. We can work out the acceleration of the Audi by differentiating the velocity. Acceleration is just the change in velocity over time. In calculus form, velocity is dv over dt. So if we differentiate this expression for velocity with respect to time, 100 is a constant, that just becomes 0, it vanishes. Minus 40 just becomes minus 4. So minus 4 is just a constant value. It doesn't depend on t or any other variable. So we've proven here that the acceleration is going to be a constant minus 4 meters per second squared. So therefore, we can just write the obvious now and conclude in the context of this question. The acceleration of the Audi is, put in brackets, a constant minus 4 meters per second squared. So it's decelerating, it's slowing down. It's accelerating in the opposite direction to travel, hence why it comes to rest eventually after 25 seconds when it gets to point B. Final part of this question, part D, is we need to work out now about the Bentley. So the Bentley's coming from the opposite end. The Bentley passes point B and travels towards A on the other track, going towards the Audi. So it passes point B with a speed of 20 meters per second and is getting faster at a constant rate of 8 meters per second squared. So find the distance from A when the Audi and Bentley pass each other as they travel in opposite directions to each other on the different tracks. Give your answer to 3 significant figures. This is quite a lot of information to take on. So in a question like this, where it's a bit more involved, a bit more elaborate, what I'd suggest we do, if we can with kinematics, is to draw out a carefully labelled and clear diagram. And so here's a diagram I'd suggest something like we might want to do. So one thing we need to do is to define a positive direction. And so I would suggest, just like the alphabet, A goes towards B. So pick A to B as positive. And so we have the Audi starting from A, going with a velocity equal to VA. Meanwhile, the Bentley is travelling the opposite direction with initial velocity here. I've just labelled it VB. So the initial speed of this Audi is 20 meters per second. I was careful to say it was the speed of it, which was 20 meters per second. But actually, if you think about it, it's going with 20 meters per second in the opposite direction to what we've said is the positive direction. And so we can say now that the initial speed of this Bentley, the initial speed U for the Bentley, is actually minus 20. It's got a speed of 20 meters per second, so its velocity will be minus 20 because it's 20 meters per second in the opposite direction to the positive direction. So now what we need to do is just consider the Bentley, which is moving in the opposite direction. So considering the Bentley, that is travelling in the negative direction. We can also think what else we're told about the Bentley at this point. So we're told about it having an initial speed of 20 meters per second. Its initial velocity is minus 20. We're also told about the acceleration. I've been careful to say it's getting faster at a constant rate of 8 meters per second squared. That means its acceleration is growing in the negative direction. And so we can say here that the Bentley is actually going forward. So it's going this direction with an acceleration of minus 8 because it's in the negative direction. So the acceleration, which is constant, is minus 8 meters per second squared. So that's the acceleration of the Bentley, A subscript B. So let's just think about this carefully now. So using calculus, we can say that the acceleration of the Bentley is negative 8. Therefore, just remembering what we talked about before, we can calculate the velocity of the Bentley by integrating its acceleration with respect to time. So we need to integrate minus 8, which is just a constant minus 8, with respect to time, and we get here minus 8t plus c. We also have some initial conditions as well to consider. We know that it passes B, sorry this finger's slightly in the way, but up here it says it passes B with a speed of 20 meters per second. Okay, so at t equals 0, its speed is 20. Its velocity at t equals 0 is minus 20. So the velocity is negative 20. So we can put this in as our initial conditions for the Bentley. So let's do this now. So when t equals 0, the velocity of this Bentley is negative 20. So therefore we can say, oops. So I know that velocity is minus 20 when time is 0. So minus 20 equals minus 8t, but t is 0, plus c. So therefore c must be equal to 0. What am I talking about? Apologies, I'm talking rubbish. Minus 20 equals 0 plus c. So c must be minus 20. I do talk rubbish at times. So anyway, we now know that the velocity of this Bentley is given by minus 8t plus the constant of integration, which is minus 20. So in other words, it's minus 8t minus 20. Now we can work out an expression for the displacement of this Bentley. The displacement we can obtain by integrating the velocity with respect to time. Now we've just derived that the velocity of this Bentley is given by minus 8t minus 20, so we can integrate this here with respect to time. So we get minus 8t minus 20 integrated with respect to time. Minus 8t, when we integrate this part here, that gives us minus 4t squared. Minus 20, when we integrate this piece, that becomes minus 20t. Then, of course, again, we need to consider the constant of integration. We now again need to think about the initial conditions. What is the case when the time is 0? Sorry, what is the displacement, I mean to say, when the time is 0? Well, when the time is equal to 0, let's have a look at this diagram again for a second and see where the Bentley is. When the time is equal to 0, the Bentley is at point B, which is 1250 meters away from A. And so we could define here point A as being where we start the velocity, start the displacement from being measured from, I mean. And so B is 1250 meters away. And so the displacement of B, the Bentley, to start with, is 1250 meters away from A. So when t is 0, SB is 1250. So we can substitute in these conditions now. So S subscript B is 1250, which equals minus 4t squared. If time is 0, that's minus 4 0 squared, minus 20 times 0 plus c. So 1250 equals 0 minus 0 plus c. Therefore, the constant of integration must be 1250. So therefore, we know that the displacement of B must be given by minus 4t squared minus 20t plus 1250. So we still haven't finished this question. We're still only about halfway through doing part D. As I said at the start, this is a harder kinematics problem. So now we need to use what we've got to think about when they'd pass each other. Okay, so when would this Audi and Bentley be passing each other on opposite sides of the track? Well, they'd pass when their displacement functions are equal, when they have an equal displacement from point A. So the Audi and Bentley would pass when the displacement of the Audi has the same value as the displacement of the Bentley. So allow me to just scroll up for a second and remind you of what the expression for the displacement of the Audi was. The displacement of the Audi was given by this expression here. So that's the displacement of the Audi, 100t minus t squared. So we want 100t minus 2t squared to be equal to the displacement of the Bentley, which we worked out was this here. So 100 minus 2t squared needs to be set equal to minus 4t squared minus 20t plus 1250. This is a quadratic equation we can solve. And so if we add 4t squared to both sides, this side would become positive 2t squared. If we now add this 20t to both sides, what we'd have here is, oh sorry, this is 100t, my mistake, 100t. So if we add 20t to both sides, 100t plus 20t, that would give us 120t. And then subtract 1250 to both sides, we end up with this quadratic here. Now, we can solve this in a few ways. We could complete the square, we could use the formula, or we could be nice and lazy and just bust out the class whiz. What I'd suggest doing is whatever makes you feel more comfortable. Personally, I'm just going to lump for the class whiz. So, I'll show you how to do this on a class whiz. So, to solve a quadratic, or a cubic or a quartic for that matter, we press menu at the top right of the calculator. We scroll along until we get to equation/func. So press equals on that option. We don't want simultaneous equations, we want a polynomial. So press 2 for polynomial. The degree of a quadratic is degree 2 because the highest power of the variable is 2. So just type in 2. Now type in the coefficient of the variable squared, in this case t squared. That's going to be a 2 because we have 2t squared. The coefficient of t is 120, so type in that. Press equals. And then minus 1250. And again, press equals. So the first value we get is 9.05. But I'm going to give that 2 more accuracy because the actual question wasn't the time when they pass, it's the displacement from A when they pass. So I'm going to give this to more than 3 sig figs. I'm going to say that's 9.0512. I'd expect that to be the only solution. How could they pass again? But let's just double check. The other solution is this. Press SROD to get it into a decimal, and you can see that's a negative time, which doesn't really make any sense. And so the time where we're going to pass is after 9.0512 seconds. So therefore, displacement from A when they pass, we can substitute this time into either this blue expression or the purple. It does not matter. So the displacement from A, I think this looks the easiest, to be honest. So let's substitute in 9.0512 into this expression. So we get 100 brackets 9.0512 minus 2 multiplied by this decimal all squared. And let's see what this gives us. So, go back to normal mode. So menu option 1, 100 multiplied by 9.0512 minus 2 times 9.0512 squared. That gives us 741.27 and so on. Now, it'd be silly to give this to a nanometers accuracy, so the old golden standard, give it to 3 sig figs. Let's just call this 741. So 741 meters. Okay, so in other words, they pass 741 meters along the track out of 1250. So a bit over halfway, so be crossing about here maybe. This is already going pretty fast when it starts. This is going at initial speed of 100 meters per second, but slowing down. This one here is going slower, but it's speeding up, so it would meet somewhere here. Anyway, and that's enough for me. Over to you now. This is going to be the final bit of kinematics you'll be practicing for year 12. So do this with gusto. I want you to try, please, questions 3, 4, 5 and 6 from exercise 11E. And do your best on those. When you get stuck, check the back of the book to double check the solutions. If you're still unsure about getting the correct solution, please do send me an email or leave a comment in the comments section of the video. Thanks again for listening, and I'll be back with some future videos. Until then, take care, and you'll hear from me soon. Thank you.